Okay, the first thing I want to do is go over the quiz, which we had yesterday. Then I will go over the homework from yesterday, and then I'm going to introduce some more interesting situations that happen with flip-flop gates, right?
Professor, I don't see a submission link for the homework for yesterday.
Really? Okay, I must have said the dates wrong. Okay, so just set your homeworks aside, and you know what? Hold on. Let me just do it right now.
Professor, I'm sorry to ask, but could you also open up 16 and 17? And possibly
Okay, this is what we're going to do. At the end of the class, I will open up the submissions for all of them, right? So at the end of the class, before we sort of leave, I will open the submissions in real time, and you will be able to submit them, right? This is, you do get credit for submission, so I trust you that you're not going to, use my solution as your submission. But yes, I will open all of them up, and we'll be able to submit everything. Because yes, the submission does count, the fact that you submit your homework. Okay, if there are no other questions, let's go on to the quiz. All right, so it was this, strange setup where you have a room with two doors, and these doors are like valves where they let movement either in one direction or the other, and to boot, each door is controlled by two switches. Now, if you think about it for a second, the two switches are really redundant, and they're intentionally redundant in a way. And again, they're numbered. So if there's door 1 and door 2, then the switches for door 1 are S1, switch 1, and switch 1, and the two switches for the other door are switch 2, and switch 2, right? So let's separate them just completely. Just the two doors do act independently. So let's just look at them separately. And when you look at them separately, what do you see, or what makes the two switches obviously redundant? Who can tell me, like, real quick? So let's look at the top blue rectangle and the one green one just below it. Ignore everything under the first green rectangle. So you're seeing there two combinations of states for the first door, for D1, right? There is switch S11 and switch S12, right? And in the first combination, S11 can be 0, S12 is 1. In the second combination, S11 is 1, S12 is 0. So what is the obvious redundancy here? We will see it, well, we will see it even more obvious in the truth table. Anyone?
Well, it's two switches for the same door, and the second digit tells us whether it's open or open in or open out, but having two switches for that means, like, there are some cases where it would, if they're both 1, then it would be both open in and out, which doesn't make sense.
Well, the other way of saying that is just, or without, which is more direct. You're right, yeah, but more directly when we look at it is that these
Do you
are
have one switch and its complement?
That is right. Who said that?
Guy.
Guy, right? So both students are right, but Guy sort of just got to the to the thing, which is that the two switches in these legal states, right? We're only, as Patrick said, that there are other states possible, but we only allow these two states, and in these two states, the two switches are always complements of each other, which makes them obviously redundant. But let's see that how it works out. Yeah. So from these legal states, right? We can because we have two doors, right? And we know what the two legal states are for each door. Right now, we can look at the combinations of what the two doors might be doing. Right. The first combination, both doors are opened in one direction, and we call it a flow up. We'll put a blue arrow there, and this is the confluence of the conditions, right? So the blue rectangle shows when D1 and D2 are open in that up direction, and we call that flow, and the condition of the problem says that this is when the light turns on. Okay.
Question, is this problem slightly different from the one we had a quiz on?
I don't think so. Well, what is the difference?
Because in this one, the circuit's supposed to light the lamp when one of the doors is open and the other one is open. One is open in and the other one's open out. But in the
Okay.
quiz, they're supposed
All
to
right.
both be open in or both be open out.
Okay, thank you for noticing. Yeah, I think I changed it in the quiz, but not on the slide. Okay, you're right. I'll explain that difference in a second, and it's not material, right? It's immaterial. So okay, so when S11 is 0, S12 is 1, S21 is 1, S11 is 0, right? We get this condition where we have flow. And with the two green rectangles, we get the opposite condition where both doors are open down and the flow is down, right? And in your actual quiz, it said that under this condition, the light is off. This slide shows that under this condition, the light is on. But it's sort of, complement of each other. The rest of it works exactly the same, right? So I think this explanation should still work, right? Yes. Yes.
No. I just misinterpreted the quiz. I thought it was saying that they both needed to be on in order for it to flow. Like, I thought it was asking what this slide was asking.
So look, so here it says, when we have the flow, in this slide it says, if we have the flow, then light is on. The other two possible conditions, the other two possible legal conditions is that when both doors are out, both doors are in, we have no flow, right? The way this slide is talking about it is L is 1, light is on here, if you see my pointer, and L is 0, light is off here. If you did it either way, it's fine. You're correct, right? It's the crux of the problem is what we'll see in the truth table in a second. The specific of the condition where the light is on or off, ultimately doesn't matter, right? If the problem is the same. It's just like two variants. Let me move forward, and if it's confusing, you can just ask me, and I'll try to go over it again. So it's in order to double check what it was in the slide, I would have to exit the presentation. I actually do believe that in the slide I say flow 1, no flow 0. So I think they actually, well, let's just confirm. Let's just confirm for sure. Greatest scope assignments. No. Okay. Okay. Quiz 2.3. Yeah, I think it actually is the same. So I changed it on both the slide and here. But look, if you misunderstood it, if you put the lamp on the right, you still get the credit. And if you if you did everything right, then the point of the quiz is still stands, right? But anyway, okay, we confirm that. If you did it using the opposite, it's just the mirror image, it's fine. Okay, let's just go back and continue. But yes, they are consistent right now. You know, as you'll see, or you probably already saw it, the problem is sort of artificially weird in order to create all of these don't care conditions that we'll see in a second. We have 4 switches, or we have 2 pairs of switches, and each pair must be complement of each other in order for it to represent a valid state. And between those restrictions, we have 4 possible states for the doors. And 2 of them, lamp is on, the green and blue, and the remaining 2, no flow, lamp is off. Okay. And these are the 2 conditions in the red where lamp is off. Any questions right now? Okay. Very good. So now let's do the first step was truth table, right? And the truth table is like straightforward. It's 4 inputs. Could have been S1, S2, S3, S4, but here they're called S11, S12, affecting the first door, S21, S22, affecting the second door. But ultimately, the doors are not represented in the function. The function is the lamp, right? So we can just copy these combinations of these 4 values, and we'll get our 1s and we'll get our 0s, right? So in this case, the lamp is on, right? So for example, here, S11 is 0, S12 is 1, so 0, 1. S21 is 1, S22 is 0. So 0, 1, 1, 0, 0, 1, 1, 0, the lamp is on, okay. And there is going to be only one other possibility for the lamp being on, right? It's this one, 1, 0, 0, 1, 1, 0, 0, 1, right? So we have these 2 states. These are the only 2 states when the lamp is on. If you misinterpreted when the lamp is on, you would get 2 zeros here, and that's fine. So now I'm going to put my zeros here, 1, 0, 1, 0, and also 0, 1, 0, 1, right? So where we have my red lines. Right? If you misinterpreted it, then you would have the opposite. You would have 1, 0, 0, 1. I have 0, 1, 1, 0. Doesn't matter, right? What matters is that the rest of them are disallowed here, so they're the don't care conditions, right? All of the other possibilities of the switches when they're not the pairs are not complements of each other, right? Or we'll say that they're don't happen, don't care, right? Never occur. Right? All of those are Ds. So now we're going to attempt, through a K-map, to come up with some kind of fewest, largest prime implicants, and then figure out the minimal form, the simplest way to build the circuit. So we only have 2 1s, and because we only have 2 zeros, well, we could put them on. Usually we leave zeros as blank squares, and then the rest are Ds. And now we're going to do prime implicants. And, Ds can be covered by prime implicants, but they don't have to be. The 1s must be covered by prime implicants. So let's see. So as you saw, because most of the board is covered with either 1s or Ds, it appears that each one can be covered by multiple size 4 implicants, right? So let's see. For example, the blue one can be covered by A, can be covered by B, by C, and one more or no, just 3?
There's
Who can tell me if there is?
There's 6, 4, 2, and 0.
That's right. Going from top to bottom, right? Because it all wraps around. Very good. So yeah, looks like 4 prime implicants covered 1, the blue one, right? Alas, none of them covered the green one, right? So we need to sort of start from scratch here. And turns out that also 4 cover it, but none of them, well, obviously will overlap with the other one, right? So what that means is that we'll have a lot of possible minimal forms, right? So we have independently 4 implicants covering the first and independently 4 implicants covering the second, right? They're all different. So how many minimal forms will this function have?
16.
That's right. Yeah, 16 minimal forms. And, well, I mean, it is what it is. Yeah. So if we convert each of the implicants in the literals, into the inputs, right? So each implicant represents a product of 2 inputs, right? And if we pick any of these minimal forms that are all as simple or as complicated as another, we basically get sum of products of 2 literals each, yeah, which is fine. Any questions about this? Right, yeah, go ahead.
Sorry, I just have a question. Can we do this like on the exam? Like, you know how you have, you didn't write out 16 minimal forms. You just kind of did it like this, like the last one. Is that okay if we do this on the exam to save time?
Yes, that is okay, absolutely. In fact, well, the bottom, right? The bottom one is okay.
Right.
Well,
right.
so if you only do the top one, you still get most of the credit. But if you want to get full credit, what you see here is sort of acceptable. You know, it's a well, it's correct. You know, algebraic, you know, Boolean algebra notation. What we have here, right, is you know, so yes, this is mathematically or whatever. This is correct. This is not just for me, but it should be for anyone, for any professor. This should be acceptable. The bottom part here. Okay.
Quick question. Oh, sorry.
Yeah.
About the beginning. I understand everything else, but just how did you determine for where you circled the blue and the green? How did you determine which one was going to be for like the flow going up and the flow going down?
Okay, so let's see. Again, it's a weird problem. I mean, let's read it. So we're designing an indicator circuit for the swinging doors, D1 and D2. So each door has 2 switches, all right, that work in the following day. If one is, let's say, 1, and the other is 2, then D1 is open in. So if it's 1 is 1 and the other one is 0, did they say 2? I meant 0. Then the door is going to be open and okay, into the room. And then if the other switch is off, and you know, if the first switch is 0 and the second switch is 1, then the door is going to be open out, right? So if we look just as these first 2 situations, they control the first door. And in the first situation, the door is open out. In the second situation, the door is open in, right? And then with the bottom 2 switches is the same for the D2, for the second door. So, you know, in the real world, or often, doors are either open or closed, period. Here, they're never closed, but they're more like valves. They're open in one direction or the other direction. And when both doors end up being opened in one direction, so meaning one out, another one in, can flow, like the traffic can flow. It's a little bit like veins work. Well, no, never mind. Right. So, I mean, there are fluid mechanical systems that actually enable this, where they can direct flow of fluid either in one direction or the other direction, right? Through a series of at least two valves. Yes.
Yeah. It makes more sense now, for sure.
Okay.
Thank you.
Good. Other questions? Basically, in the end, the task is actually not as hard as like the weirdness of the of the wording of the problem. So I'm sorry about that. Okay, but when you have, let's see, these circuits, right? They represent some kind of real world condition, right? And you're handed this real world condition, and then you need to express it in Boolean logic. And there is going to be always a challenge of translations. So it's not like just completely, arbitrary. Anyway, okay, let's continue. So we did that already. Now we're going to move on to the flip-flops, right? So was I introduced you to the standard flip-flop, or one of the standard flip-flop gates implemented through NOR gates. And then I also gave you the different implementation of the same thing through NAND gates, and you were going to build a truth table about it at home. So let's quickly go over that, and then we'll move on to more interesting flip-flop gate situations. So on the exam, I will have problems that are just easier to understand in English than that one. Okay. All right. So there is our. So and again, we want to for it to be a valid flip-flop gate, when there is no signal, when S and R is 0, it should preserve the previous state. So we can confirm that. Now there are two possible previous states. Let's say that Q was 0, right? And then these inverters will make the absence of signal into signal. So if Q was 0, and the inverted signal is 1, the whole thing is, the AND is 0, and the inverted 0 is 1. So the state is preserved, and then we can keep going from complement of Q, this 1 goes in here. The inverted 0 is 1, so we have two 1s going into the AND. It's 1, inverted is 0. Right, so we can keep, round and round and round, and as long as the two inputs are 0, this previous state will be the same, right? If the previous state was the opposite, right? If Q was 1 and Q prime was 0, again, it would stay the same. It's sort of like mirror image. If you need me to trace it, tell me, and I'll trace it. Otherwise, I can move forward. Okay, right, so we have satisfied ourselves that it will hold its value as long as we don't send any signals to it, which is already, the most important thing about flip-flop gates. But now we need to also check that we can set or reset its value to something that we want. So first, we're going to set a signal to reset it to whatever it was to make it 0, right? So the R will get a 1. Okay, there it is. So I'm moving too fast. So when R got a 1, the 1 became inverted is 0. The 0 goes into the AND. No matter what the other input was, this AND becomes 0, and then inverted 0 becomes 1, right? Which is what we would want, right? When we reset Q to 0, its complement would be 1. But let's keep going. That complement 1 goes into this AND. There was no signal to set, so it's 0. Inverted is 1. So we have two 1s going into the AND. AND is 1. Inverted 1 is 0, right? And we achieved what we wanted. We sent a signal to reset, and it reset Q to 0. And of course, complement of Q is 1. So that's good. And then now, after that, in the next cycle, we're going to set it to 1, right? So we're going to, send the 1 signal to S, and of course, we're not sending anything to R, right? We don't want to send conflicting signals. So if S is 1, inverted 1 is 0, the 0 goes into the AND. No matter what else goes into it, the AND is 0. Flipped 0 is 1. So the bit is set to 1. Good. And then when we keep going, this 1 goes into this AND. There was no signal in R, so it's 0. Inverted 0 1 is 1. So we have two 1s going into the AND. AND is 1. Inverted 1 is 0, right? So as it should be. When we set the bit to Q, Q to 1, then complement of Q is 0. And then we promise never to try to set and reset bit at the same time. So we're not going to do the last one, right? We don't want that. Because if we did try to do that, then both Q and Q prime would become 1, which makes no sense, right? They will not be complements of each other anymore. So we're going to exclude this possibility from our truth table. We'll just get rid of it, not allowed. So our truth table becomes very compact. So we can have previous state without signals. We can reset it to 0, or we can set it to 1. So that was the homework. That's it. Any questions? Any questions? OK. So from now on, going forward, we're not going to worry about how the flip-flop gate is implemented. Was it made with NANDs? Was it made with NORs? Doesn't matter. It works. It works. And we're going to, right, because before, well, in most slides, and I told you also to do it, once you make it, you put a green box, or you put a box around it, right? So now we're going to just see it as a box, right? It's a box that works correctly inside. And what we have, the box has two inputs, set and reset, and two outputs, Q and Q prime, right? And we just trusted that it, works correctly inside. So we know that when we set, Q becomes 1, Q prime becomes 0. When we reset, Q becomes 0, Q prime becomes 1. And we were going to treat it that way. Any questions? OK. So let's look at what is called a D flip-flop. Right, this is closer to what happens in real life. Right? So let's look at it. Here we have our regular flip-flop gate, but there are some other externalities involved. Right? Well, the biggest important externality is that in real computers, everything is done on a system clock. Right? So we're going to treat the system clock as a controller, right? So we learned about controllers and controlled input 2 days ago, and here we're sort of using that knowledge, right? So the way we're going to plug it in is like this. The idea, right? What is D? D is going to be some kind of data, right? It's going to be, could be anything, could be 1 or 0. It's a value that we want to assign to this bit of memory, to this flip-flop gate, right? So totally legit, D could be 1, could be 0, right? And the whole point of having a flip-flop gate is that we should be able to save that 1 or 0, right? Okay. So so we have a bit of wiring before that D goes into our flip-flop gate, right? So what we're going to do, so we're going to put a splitter, right? And we're going to split. We're going to direct the true value of D into set and the complement value of D into reset, right? That's what we're doing. Now, forget about the clock, forget about the controller for a minute. Can somebody tell me what am I doing? What I'm doing here? What's going on? Well, we have D, whatever it is. Then I'm splitting it, and I'm sending its true value to set, and then I'm inverting its value and sending that to reset. What's the point of that? Why am I doing this? How does this make sense?
You're ensuring that set and reset are never the same value.
Yes, I'm definitely ensuring that, right? So I'm ensuring a few things. I'm ensuring that, that S is definitely always going to be complement of R, and thus I am ensuring what I had in my truth table. Okay, never mind.
Oh, so you're making sure that you don't have the 1-1 condition?
Well, yes, that is true indeed, as the previous student said. If they're always complements of each other, I will not get the 1-1 condition, which I definitely don't want. And I'm actually physically ensuring that it will never happen. And I'm also ensuring that 0-0 will not happen, even though previously we allowed for that possibility. Is that okay? It's not. Sorry, I'll just start from here. Right, so both students are exactly right. We're ensuring that neither 1-1 or 0-0 inputs will happen to set and reset. Or in other words, we're ensuring that if set is 1, reset will be 0 necessarily, and if reset is 0, then set will be 1 necessarily. But is it okay that it seems that we somehow made sure that S and R never both zeros? Well, hold that thought, right? So if we just had D going in S and R directly, then yeah, we would never get that S and R being both 0, right? And why do we need to have situations when S and R are both 0? Why do we need that? What happens when S and R are both 0?
Doesn't it mean that it hasn't been turned on, or nothing has been, there's no input? You mentioned this yesterday, but I don't remember what exactly you said.
Well, that's exactly right. When both are 0, nothing happens, right? And why is that important? Why do we need to have this possibility of nothing happening? What is the goal of having a flip-flop gate? Is that when nothing happens, its previous state doesn't change.
It's stored.
Yeah, right. So we need to have this possibility of both input 0 in order to actually preserve this previous state until we are ready to change it, right? So we achieve that by having the clock, right? So the true D going into S and the inverted D going into the R are here on the circuit. They're sort of interrupted by AND gates, right? 2 AND gates. And what they're ended with is the controller or enable or clock signal, right? And in a second, we'll see how the clock signals, it's sort of like passage of time. But whatever it is, it's going to be either 1 or 0. Right? And when the clock is 1, right, then whatever is going into this AND is just going to be ANDed with 1, and it will be identity. Okay. I apologize, but I need to let in the plumber into the apartment, so I'm going to pause the lecture. Just take this moment to look at the slide. I have to let the plumber in. Apologies. Just bear. Okay, I'm back. Thank you for bearing with us. Okay. So when the controller signal is 1, right, then we have the true value going to set and the complement going to reset. However, when the controller value is 0, right, whatever else is going into the AND gate is zeroed out, right? So when the controller or the clock is 0, that is when we will get the situation where both S and R are 0. Any questions about that? No questions. Okay. So looking at the clock values, which inputs are allowed in the SR flip-flop, right? So if S is D and R is complement of R and clock is 1, right? Those are 3 possible inputs. Or if clock is 0, both S and R are going to be 0, right? And the problem of input 1, 1 is avoided, right? So in the previous, and when we looked at the flip-flop gate previously, we had to say, oh, we're just not going to allow 1, 1. Well, here we're physically preventing it from happening. Okay, so now the truth table becomes very small, right? So, and it only depends, actually, this particular truth table, on the control input, right? So the clock, the controller, can be either on or off, 0 or 1. And if clock is 0, right, then nothing happens, nothing changes, and the previous state of this flip-flop gate is preserved, right? So memory is preserved. However, if the clock is on, ding, then the flip-flop gate, the Q, assumes the value of D, whatever that value is, right? So when we're looking at it, like in reality, in real life, the clock or the controller will have ostensibly 2 outcome, previous state or value of D, right? But of course, previous state is some value 1 or 0, and D is also some value 1 or 0, right? Any questions about this? In other words, when clock is 0, we're preserving the value. When clock is 1, we're assigning new value. This new value may or may not be the same as the previous value. Does that make sense? Can you still hear me?
Yes.
Yes.
Yes, that
Okay.
enables us to change the value every clock cycle.
Yeah,
what's
I mean, and that's usually what happens, right? You want the calculation to keep going. And yeah, it may be a different value, a new value, and the specifics of it, will be, let's say, when you write a program in assembly, every operation does something with a particular register, right? Well, here where a register will hold like a byte or several bytes, but here we're looking at individual bits. But yes, what we're looking at here is that the value gets updated in every cycle, but it gets saved during a cycle. Right? And we will see right now specifically what that means in sort of microscopic time. Right? So here's another way of drawing the same thing, right? This D, it could be further back. It doesn't matter, right? We just know that S and R, right? We have the same S and R inputs that are complement of each other. Here it's ensured from splitting D and inverting one of the branches. Right here we just see S and R. Same thing, right? And what is also the same is that we have the clock, and here I just call it clock. Right? Does everybody see that these are pretty much the same? Yeah.
Yeah.
Okay.
Instead of having what's called the inverter, you just make sure that S and R are never the same value.
That's right, and and this is just one way of doing it, and presumably to the left of this diagram, something like that happens. Okay, but it's the same thing, and we're going to look more closely of what this clock does and how we represent it. Right. So now that we have this more or less equivalent diagram, now I'm going to sort of push. I'm going to take these two AND gates, right? So I have S, R, clock, and then there is a splitter, one splitter and two AND gates. And I'm going to just like push that into the circuit. I'm just going to push it in from the left into the black box, right? Now that I only see the inputs, I see set, reset, and clock, right? They're all going into this flip-flop gate, and we'll just call that a clocked flip-flop. Did this make sense? Right? It's just I take this chunk of wiring and just push it into the box. Right? It's still there. It's just that I don't want to see it. Okay. Here, input 1, 1 is avoided only if S is complement of R, which is usually the case, or we'll just say, as far as we're concerned, it's always the case. Right? If we want to make sure that that is always the case, we'll put something like this, split invert outside, but we'll just trust that it's the case. Okay, so now we can make the truth table. It's going to be very similar to the previous truth table because it's more or less the same thing. So the clock, right, which is the signal that we care about, the controller, could be either 0 or 1, right? And if the clock is 0, Q, or the flip-flop gate, maintains its previous state, but when it's 1, it will get the value of S, the value of set, which could be 1 or 0, right? So, and the only way set could be 0 is when. So ostensibly, I have 3 inputs, S, clock, and R. And yet, in this truth table, right, I only have an input of clock. And then here, when I have the function, I have either some kind of previous state, or here I have S. And I tell you that S could be either 1 or 0. So if S were 0, what does it tell us about R?
It's one.
Somebody's
to be
mic.
one.
It's one.
Yeah, somebody's mic. You can turn it off. But yes, both students say correctly, exactly right. Yeah. If S is 0, it means that R is 1, right? Which is, we're setting the whole thing to 0, right? So in any case, yeah, if S is 0, then Q is 0. So this truth table, the very compact truth table, becomes sufficient. Yeah. And another way to think about it is that because it's a little bit like with the redundant switches on our quiz, right? Although we have technically 3 switches, oh boy, 2 of them are redundant, right? But we do want this redundancy in order for our circuits to work. But yeah, if S is 0, then R has to be 1. If S is 1, R has to be 0. So effectively, they're really only two inputs, clock and anyway, right? So you can try to think about it in different ways. Or, right, I said really two inputs. However, with the function Q, right, in this truth table, we don't care whether it's 1 or 0, right? We only care whether it's a previous state or a new state coming from S. Right? And because S, the value of S, is a valid outcome for Q, right, then really there is only one input, and the input is clock, right? And for that reason, we only have 2 rows in this truth table. How about that? Are there questions about that statement?
I think the concept makes sense, but is there like a real world example where we'd use something like this?
Yeah, the real world example is going to be that your computer is doing calculations, right, in real time, and these registers they have to change their value pretty much on every clock cycle, right? So we're not talking about hard drives where we're going to save something for a year and not touch it, right? This is operating. No, this is not even operating memory. This is the processor, right, where we have registers that are performing operations. And we do want the value to be preserved during a clock cycle, but you'll see it in the next slide. At the next clock cycle, it should be able to accept a new value, right? And that's what it does, right? So on the off cycle, it will preserve the previous state. On the new cycle, it'll accept the new state, whatever it is, could be 1 or 0. So I think that when we look at the next slide, when we actually see the clock, and you recognize it, we've seen it, I showed it to you in the very first class. We'll see sort of like more hands-on what happens. So your question leads us into it. So the previous one was a D flip-flop, now a T flip-flop. So here we're making it very explicit, right? So we have inside the box with our clocked flip-flop, right? So the regular flip-flop had just S and R. The clock flip-flop is the regular flip-flop with S and R and the clock outside with the 2 ands, right? And then I said I pushed it in to review it. You can go back to previous slides. Now it's inside, and we call that a clocked flip-flop, right? So where we have set, reset, and clock. But I told you that the real kind of input here is the clock itself, right? That creates the 2 rows of the truth table. And what we'll do to ensure that set and reset are complements of each other, we're going to feed back the Q and complement of Q back into them. Right. So if Q was, let's say 1, then 1 goes into R. And then because of that, Q prime is 0, and that will go into S, or the other way around, right? But the variable input, or the input that we control, is the clock. Okay. So we will represent the input, namely the clock, as a diagram, time being one of the coordinates, and 0, 1 the other. Right? So the diagram is below. You'll see it in a second. Notice also that I put this whole thing into a green box, and now I have a single input and 2 outputs. The 2 outputs are complements of each other. So what we'll see in a second is, well, a diagram where we see the clock, which is the one axis, which is time. And the other axis, up and down, is going to be the bit values. So they're going to be discrete, either 0 or 1. And that is what we have here in the little set. Now, we want to give a corresponding diagram for the output, right? The Q, right? So we're going to initialize clock to 0 and Q to 0, which means that Q prime is going to be 1. So this is the diagram, right? When we go from left to right, this is the passage of time, right? And it oscillates the clock, right? If you remember, we have the low voltage state, and then we have a surge to goes higher voltage state, right? So I don't know if I said, but so far we've been talking about signal on, signal off, or electricity on live or not live. So in the real world, to have that kind of switching would take too much power, burn too much electricity, generate too much heat. So in the real world, rather than completely turning things on and off, we just change the current just a little bit. Like there is the low state, high state. So we're going to start this diagram in the low state, and the Q is 0, right? But then with the clock, it will oscillate. It will just cyclically sort of like hit it into the higher electrical state, right? And it's this ramp on the red bits, right? So every time it, you have a more juice going in, it goes to that higher state. It happens in that moment. Right? And when you look at it, it looks like it stays in the state of 0 or state of 1 longer than it takes time to change the state. Yeah, and it's true, but this is not representative of the real world. So in the real world, the processor does, a processor clock, let's say, does 1 billion, cycles a second, right? So that means that one cycle will take, from red to red, will take, let's say, 1 nanosecond. But this ramp on, the switching of the voltage, right? It will take at least 1,000 times less time to happen. So this ramp on in real life is very steep, almost square, but not quite. So if the whole cycle is 1 nanosecond, then the moment of signal switching up, it will take 1. What is it? Pico. It will take 1 picosecond, right? So 1,000 times less. I think so. So 1 picosecond is 1 trillionth of a second. So any questions about that before I continue? This is just put it in the context of real life. Okay. So moving forward. So that is the diagram for the clock, right? How it switches from 0 to 1, 1 billion times seconds. And then here, in the same time, we have the Q, right? Which is the state of the flip-flop, right? And again, we started with 0 as well. And now let's actually trace it. It started at 0, and then when we got to that first red moment, when the clock switches to 1, the clock became 1. Boom, so the 1 got sent in. So it is the rising edge, red, of the clock that acts as a one input to the clock SR flip-flop. Okay, so at any point, if it's unclear, stop me and ask me. Let me just check that we have time. Okay, we have time. Okay, good. And we started on time today, right? Even though I had a lecture before, so that's great. All right. So now, outside the rising edges, clock acts as zero input to the clock SR flip-flop, right? So even though the power state at the top here stays for some time, the impulse only happens during the rising edge. For the rest of the phase, or for the rest of the period, let's call it, right? For the rest of the single period of oscillation, there is no new signal going into clock, so we consider it zero. Okay? Okay. So that is, input clock will only enable the SR flip-flop during the rising edges of clock. Now, we exaggerated the duration of the rising edge of the clock to show its importance, right? As I said, in real time, it happens incredibly fast, 1/trillionth of a second, and then for 1,000 or 999 nanoseconds, it just sits there, but still very fast. Okay, so what happens to Q? The moment the one signal is sent here, right, Q becomes 1, right? Why? Or Q, sorry, we started with okay. So let's follow. Q was 0, right? So that's how it started. Q prime was 1. So when we sent the one signal in here, the 0 from Q went to R, and the 1 from Q prime went to set, and that set Q to 1 and Q prime to 0, right? And you say, oh, but now Q prime will go into set, but it won't. It will not go until the next, until clock hits 1 again, right? So for now, Q is going to stay as 1 at least until the next clock cycle starts. And when the next clock cycle starts, right, that 0, let's say from Q prime, will go to set, and the 1 from Q will go to reset, right? And then the clock will signal 1, right? That will end both of them to 1, and the Q and Q prime will switch now. And so this is what I just said happened, and Q prime, Q will got back to 0, Q prime to 1, right? I will go over the slide again, right? But we can continue. Right? So again, there will be no changes until the next, ramp 1, until clock has a 1 signal again, which happens here. And that is when Q will change again. And now it'll switch to 1. And it'll stay, yes?
What's the purpose of like the different flip-flops? Like, isn't one flip-flop enough? And isn't this flip-flop, it seems like worse than the other one because it takes time for it to change?
That's an interesting question. So we have been leading up to this flip-flop, right? Because we are the flip-flop that exists by itself is not very useful, right? We have to integrate it into an actual processor, right, where things unfold, in time, right? And the time is represented by the clock, right? And what we're seeing here is that whatever the clock is, this becomes apparent now if you look at this diagram, is that this flip-flop gate is going to be only half as fast, or for that matter, any flip-flop gate, right? So this is the fastest possible flip-flop gate is going to be only half as fast as the system clock, right? So if you look at the oscillation at the phases of the oscillation at the length of the period, you're seeing that the Q signal oscillates at the speed that is half to twice slower than the clock input, right? And this is sort of it for the flip-flop gates, right? The only thing left is the race there is an example of a race condition that I'll quickly cover tomorrow, and then we'll do a little bit of review. But right now, let me go over this slide one more time so that we follow what actually happens. Now, before I do, ask me other questions so that I keep them in mind.
So we've built up to this flip-flop gate and we need to use the clock because it's more efficient than trying to switch on and off the electric current. Is that right?
No, that was a bit of information that I guess really was not necessarily necessary. It was just like, I wanted it's sort of like informative. So okay. Why are we? Well, I suppose it is related. Why are we talking about oscillation? Because that's how electricity exists in real life, right? So, for example, if you plug something into the wall, it's AC current, it's alternating current, right? And it goes in sort of a sine wave, right? So we call that in physics, the difference of potentials, the voltage, right? It fluctuates like that in a predictable, synchronized manner, right? So the AC current is 60 hertz, right? So meaning that what the electricity flows, in your receptacle and then goes into your microwave or whatever it goes like that up and down 60 times a second, right? And then, or it goes into like a regular old school Edison light bulb, not the LED, but the regular light bulb. If you took I don't know, if you have a fancy phone that can film at very high speed and then slow things down, you can film your light bulb and then slow it down, and you see it will flicker. Too fast for you to notice, naked eye, but you'll see it flicker if you slow it down. And you'll see that the Edison bulb flickers 120 times a second, right? Twice as much as there is as the frequency of the current, because it will flicker both on up and both on down, whatever. So that's now here we're talking about also oscillation of electrical signal a lot faster, I don't know, a billion times faster. Unlike the Edison bulb, only the phase where it goes up, where the voltage increases, will be interpreted by our hardware as a 1 signal on the clock, right? And the rest of the cycle, all of the other phases of that cycle, will not be interpreted as 1. They will be interpreted as 0, right? That means that now, did you need to know about the electricity of it? Not necessarily. You just know that the clock essentially sends a ping, once in a cycle, and the cycle is 1,000 times longer than the ping, right? So the ping does something to the flip-flop, and then it waits for 1,000, so, let's say it took a second to ping, and then it waits for 1,000 seconds, and then a second to ping, and it waits. So I will go over the sort of like the steps internal on the clock in the flip-flop in a second. But what you're seeing here, right, is that where the clock goes from 1 to 0 on every cycle, goes 1, 0, 1, 0, 1, 0. The state of the flip-flop gate, the Q, can only change once every cycle, right? So it goes from 0 to 1, then back to 0. So to go back to 1, it needs 2 clock cycles. So you're going to
same for not Q.
Yeah, right. So if Q is whatever Q is, not Q is the opposite of that. So we only sort of have the not Q in order to feed it back into S, right? Ultimately, we consider Q as the state of the flip-flop gate, right? Q is the bit that is stored in it. And of course, complement of Q is the complement of that bit.
But if you had to draw the diagram for not Q, would it start at the top, and then in the first flip it'll go down?
That's right. We could do a diagram for not Q, and it would be the mirror image of the Q. It would be the mirror image of the Q, and of course it would move at the same speed, right? It would start, high, then go low, then stay low, then go high, then stay high, and then go low, stay low, go high, and etc. Okay, so let me just sort of very quickly review it, right? So we have just the flip-flop gate. Let's see if I can make it bigger without. We have fit in the window. Okay. We have just a flip-flop gate with set and reset signals. Okay. Then we now plug the clock into it, and we say that, oh, this flip-flop is only going to change only when the clock is sort of on, right? At every other moment when the clock is not on, not enabled, whatever, the flip-flop gate will not change. So the Q will remain the same. So when we can say interchangeably the value of the flip-flop or the Q, right? We're talking about the same thing. Q is the value. Okay. And then when we have the clock and some kind of input, doesn't matter what it is, right? We really only are looking at the clock input, right? So clock is 0 or 1, and if it's 0, no change. If 1, it is whatever the value of set, right? So it will change to 1 if set is 1. It will change to 0 if set is 0. Why? Because when set is 0, reset is 1, right? And that makes reset it to 0. Okay, then we take, let's say, this wiring where we have the clock input, then it sort of ANDs, A and D, ANDs with set and reset and goes into set and reset, right? And we're going to push those wires into the box, right? And now we just have 3 wires going in, set, clock, and reset. And that leads us to the T flip-flop, right? Where we're going to wrap back Q into R, into reset, and complement of Q into set. And the only external input we have is the clock. Right? So let's do this one step by step. So this is our T gate, T flip-flop. So we will represent the input clock as a diagram, time being one of the coordinates, and the value, either 1 or 0, or the high or low level of current will be the other coordinate, the y to the x. We want to give the corresponding diagram for the output Q, where we will initialize clock at 0 and Q at 0. So we have the clock starting at 0. Eventually it will rise to 1 right here. And there is the Q, also starts at 0. And so here Q starts at 0, so Q prime will have to be 1. Okay. Now, boom, clock, in time, the new cycle starts, and this red moment when the clock gets signal 1. At that point, the one from the clock is here, the one from the Q prime is here, and the 0 from the Q is here. It is the rising edge of the clock that acts as one input to the clock SR flip-flop. Right? So the moment that this one input goes into the clock, then the other inputs that internally get ANDed with it, start going. They get going. So complement of Q goes into S as 1, and then Q goes into R as 0. These outside the rising edges of clock, it will act as 0 input to the clock SR flip-flop, right? So after this red ramp, clock is 0, and that means that whatever S and R are, it will be they will be both ANDed with 0, and will be 2 zeros, right? Both S and R will be 0, and that means that the Q will not change while clock is 0. But when clock is 1, right, then let's say if we started from 0, Q prime was 1, so S is 1, and that means that Q will be set, right? Q will become 1, and Q prime will become 0. And Q becomes 1, and Q prime becomes 0. Now, but that means that S will become 0, right? And you think, oh, then now it should change back. Why will it not change back immediately? Why will this flip-flop not? Yes.
Because the clock needs to be 1 for it to change again.
That's right. So that 0 will sit there at S, but it will not actually change anything until clock is 1 again. And when clock is 1 again, then, well, the 0 will remain 0, but then when S is 0, R is 1, and that will be ANDed with the clock, and then it will go into the flip-flop gate, and it will reset it, right? It will reset Q back to 0. So Q is going to continue to be 1 up until here, where it will get reset to 0. Yep, there Q got reset to 0. Q prime became 1. Now S became 1, which means that, oh, it's going to go back to 1, well, but not yet, right? It will have to wait until the next clock cycle, right? So it will stay 0 until this next clock cycle. Now we already have 1 in the set in the S, right? It will get ANDed with the 1 in the clock, and the Q will become 1. And Q prime will become 0. Right? So Q became 1, and it's going to continue to be 1 until here. and then it will become 0 again. And we're seeing that these flip-flop gates, are going to be exactly half as fast as the system clock. Right? And then when you take computer architecture 2, you're going to be working more with these things. So this would be called a synchronized circuit. So let me just show you really quickly. Well, first of all, are there any further questions about anything so far?
Why is it called a synchronized circuit?
Because it's synchronized to the clock, right? And the clock it's moving at a predictable speed. Okay? So what we were looking at before was just sort of like asynchronous circuits, where they don't really exist in time, but this one does, right? So we go from these asynchronous circuits to controller, right? And then the controller or control circuits, and then we use clock as the controller. And once we start doing that, it becomes synchronized to the clock. So if we look very quickly at the at our outline, right? There are readings that I would like you to do, right? Definitely 411, where we have the multiplexers for control input and the storage elements, and then race conditions, right?
The link for race conditions doesn't work. When I click it on my computer, it just has a
What
blank.
if you refresh? What if you what if you do like control refresh, or like there's basically, it means that your computer stores the old version of the web page. Do you want to do it right now? Are you on Mac or Windows or Linux?
I'm on Windows. It's working for me.
So the person for whom it's not working, who is that? Right, so Jordan, is it working now?
No, it's not working. I can try restarting my computer after the lecture.
Don't restart your computer. So when you click on it, what do you see in the URL?
I see search storage.techtarget. I see the same URL that you have, but my screen is just black with a dot.
Interesting. So yeah, that must be something with your browser situation. But you can also just Google it. I mean, this is an article, like it's not in your textbook, but this is an article that I think is sort of.
Is it because I'm using Chrome? Oh,
I'm
no,
using Chrome.
okay. It works when I repaste it.
Okay, good. Okay, problem fixed. So let's take a quick look at what, I mean, I'm going to, it is going to be tomorrow's lecture, the first part, but let's take a quick look at it now. It's going to be iCloud Keynote. All right, we still have a few minutes. Oh, actually, there's something we need to do. There's actually something we need to do right now. Let me see. Why don't I see it? Okay, so let's leave tomorrow's lecture until tomorrow, but there is actually something that I will ask you to do. A few days ago, you have received emails about teacher evaluations, right? So let's take a moment to do them now. So obviously they're completely anonymous. I will not see even the aggregate value of it until sometime in the fall semester. So this is completely anonymous. There's no way for me to see the review that you give me. But did you receive those emails with the link?
Yes.
Yes, I got one.
Yeah, so let's take the time now to review to do them. Why am I asking sort of so forcefully? Because the administration wants the instructors to get at least a 50% response, right? It is not. Yes, they look at our review, but if we don't get a 50% response rate, they give us a talking to. So they basically want to hear back from students, yeah, so I would be very grateful if you just did them now and then be done with them. And again, there's no way for me to retaliate. If you give me a better, I hope I did okay. But yeah, let's just take a moment and just do them. I do that. Well, I have to do that every semester in every class that I teach. It's usually really like pulling teeth in the large lectures, which is most of the courses that I teach that are, like 200 people or more. And well, I don't know. Let me show you something. If we go to Gmail, you know what? Let me stop sharing so that we don't need to share. But don't leave. I want to show you something cool. Okay. So I will share my screen again. I'll share my screen again. So this is the only thing that we can see, right? And the only thing that I will be able to see until sometime next fall. And that is how many of you have submitted. I know that you're all working on them now, but when it's a large class, I just sit there with them for 15 minutes, keep refreshing this thing until it reaches 50%. So I'm very grateful for you actually taking time and doing that. All right, it doubled. Don't stop sharing. Let's All right, we just got to 20%. All right, we're at 23%. We're doing this here also being helpful to other students, right? So if we look at it and we see that, oh, the grades are generally good, but it looks like I don't know, the professor could be, I don't know, more respectful to the students or something, right? So then based on that, the professor will sort of like adjust their manner, or like, oh, the professor isn't, I don't know, clear enough or doesn't spend enough time on certain, I don't know, concepts, right? And then that professor, if he sees that their rating is a little lower in that rubric, they will try to, maybe not move as fast in their lectures, right? So, you're by giving these, ratings in specific categories, right? You're actually giving the professor a chance to improve the way they teach, which will have their help their future students. And likewise, the students who are now reviewing the professors that you will have next semester, you will benefit from them. So far we have 8 students out of 30 who submitted the reviews. Okay, I will stop recording, but let's